see this problem. A normalized wave function is given by psi of x equal to a e power minus alpha x, where alpha is a constant whose value is greater than 0. Then find the value of a. Here psi of x is a normalized wave function. We know the normalization condition. Psi star of x, psi of x into dx equal to 1. Here the limit is minus infinity to plus infinity. If you consider the wave function value psi of x equal to a into e power minus alpha x, then psi star of x, psi of x dx is a square e power minus 2 alpha x into dx, which is equal to 1. Here the limit varying from minus infinity to plus infinity. Psi of x is a e power minus alpha x, then psi star of x is equal to a star e power minus alpha x. A star equal to a square, then e power minus alpha x into e power minus alpha x is e power minus 2 alpha x into dx equal to 1. Now this is modified as a square 2 into, change the limit, minus infinity to 0, then 0 to infinity. If you interchange the limit, minus infinity to plus infinity into 0 to infinity, we have to introduce 2. E power minus 2 alpha x dx equal to 1. Now we have to integrate this. A square into 2, then e power minus 2 alpha x divided by minus 2 alpha. Limit varying from 0 to infinity is equal to 1. See here, e power minus 2 alpha x dx integral is e power minus 2 alpha x whole divided by minus 2 alpha. Now you have to apply the limits. 0, lower limit, infinity is the upper limit. If you apply the upper limit, you may get 0, minus of lower limit. Already one minus sign is available, so minus to minus plus. If you put x equal to 0, anything but 0, 1. So we can get a square 2 into 1 divided by 2 alpha. See here, if you put the lower limit, upper limit is 0. If you put the upper limit, entire is vanished. This minus sign is available. Minus of lower limit, minus into minus plus, lower limit is 0, anything but 0, 1. So 1 divided by 2 alpha, which is equal to 1. So a square divided by alpha is equal to 1. Then a square is equal to alpha, a equal to root alpha. This could be the value of a. When we go to the second problem, for a particle, for a free particle, the wave function is given by psi of x comma t, which is equal to e power I into k dot x minus omega t. What is the value of kinetic energy in terms of H cross and K. See this problem. Here a wave function is given to you, psi of x comma t, which is equal to e power I into k dot x minus omega t, which is a plane wave equation. For a free particle, the potential energy is 0. For a free particle, the total energy E equal to E square divided by 2m. This is nothing but our kinetic energy, because potential energy is 0. Kinetic energy is half mv square, m square v square by 2m. mv is our p, so p square divided by 2m is the total energy. In this case, the propagation vector k equal to 2 pi by lambda. According to de Broglie, lambda equal to h divided by mv. Therefore, k equal to 2 pi divided by h into mv. This 2 pi by h is our 1 by h cross. M into v is our t. So k equal to p by h cross. Then p equal to h cross k. So instead of this p, we have to put h cross k. So E equal to h cross k whole square divided by 2m, which is equal to h cross square k square divided by 2m. This is value of kinetic energy in terms of h cross and k. Now we will go to the third problem. If a wave function psi of x is an eigenfunction of momentum operator P equal to minus I h cross dou by dou x. This is the x component of momentum. What form must psi of x take? They are given x component of momentum and are asking about the eigenfunction. We know the eigenvalue equation. An operator operating on a function gives one eigenvalue p and the same eigenfunction. This is operator. This is eigenvalue. So an operator operating on a function provides some number and the same function. This is called eigenvalue equation. Now our operator is minus I h cross dou by dou x and is allowed to operate on the function psi of x. Then we may get eigenvalue, that is p is a number and psi of x. This is our eigenvalue equation. Operator is given to you, that is x component of momentum operator, minus I h cross dou by dou x. This is an operator which is allowed to operate on the function psi of x and gives some value, that is a number, eigenvalue, and the same function. Then only we can call this one as an eigenvalue equation. Here we may modify this equation, dou psi of x divided by psi of x, which is equal to p divided by minus IH cross into dou x. See here, dou psi of x divided by psi of x. P in into dou x all divided by minus IH cross. Now you have to integrate this equation. If you integrate this left hand side, see here, if you differentiate psi of x, we may get our dou psi of x. So the formula is log of the denominator, ln psi of x, which is equal to P divided by minus IH cross into x plus constant of integration C. This is ln psi of x, which is equal to multiply I by I square is minus 1, already a negative sign is present. So I P divided by H cross into x plus C. This is the value of ln psi of x. Now we may find the value of psi of x. Psi of x equal to e power IP by h cross into x into e power c. Put a equal to e power c or e power c equal to a. Now the value of psi of x equal to a e power I p by h cross into x. This is the value of the wave function. It's all about the solution. Now we will go to the next problem. Consider the normalized wave function psi of x. Consider the normalized wave function psi of x, which is equal to 2 by a inside the root sin n pi by a into x for x greater than or equal to 0 less than or equal to a. Find the expectation value of position for the ground state n equal to 1. This is a wave function corresponding to a particle in a box. If you consider the width of the box is equal to a, then the expectation value of position in the ground state n equal to 1 should be evaluated. Psi of x is given to you. For the ground state n is equal to 1, then we may write psi of x equal to 2 divided by a, which is our normalization constant, the sine n pi by a. Here n is equal to 1, so pi by a into x. This is the value of psi of x for the given condition. For the ground state, n is equal to 1. You know the expectation value of an operator, which is equal to psi star of x, then the operator value psi of x into dx. For the normalized wave function, this is the formula for expectation value. Here the value of psi of x is given to you. Psi star of x is also the same. Therefore, this is equal to x into psi of x square dx. Now we have to find out this. Here the limit is 0 to a, which is equal to zero to a x into 2 by a, then sine square of pi by a x into dx. Now you have to solve this. For that, we have to use the formula sin square theta equal to 1 minus cos 2 theta whole divided by 2. Then expectation of x equal to 0 to a x into 2 by a. Then instead of this, you have to put 1 minus cos 2n pi x, 2 pi x, not n, 2 pi x by a whole divided by 2, entire is multiplied by dx. See here, this is theta, pi x by a, 1 minus cos 2 pi x by a whole divided by 2. Now we may separate this into two integral, 0 to a x 2 by a dx whole divided by 2. This is first integral. See here, x into 2 by a 1 into dx by 2. Then minus of 0 to a x 2 by a into cos 2 pi x by a whole divided by 2 into dx. This is the second integral. If you evaluate the second integral, the value is 0. Just concentrate on the first integral. See, 1 by a, say 2 it cancel, 1 by a x square by 2. If you integrate x dx, you may get x square by 2, then apply the limit 0 to a. This is equal to, here also you may put the equal to symbol, or it may be confusing. The problem is inadequate space. Expectation of x equal to, the second integral value is 0. You may prove it separately, no problem at all. Then 1 by a integral x dx, which is equal to 1 by a x square by 2. Now apply the limit 0 and a. Here lower limit is 0, upper limit is a. A square by 2 by a, which is equal to a by 2. Therefore, the expectation value of position is a by 2. This could be the answer. So we'll discuss the rest of the things in the next lecture. Thank you.